Okay, we're in the process of relating the motor characteristics to the electrical requirements for a motor, and we're on our way to sort of to being able to explore the efficiency of a motor. We're going to have the ability to calculate the energy input to the motor and then the rotational energy output of the motor, and we're going to be able to kind of grade any given motor in terms of its efficiency of operation. So we're just building towards this. So we have some previous knowledge. What we know from before is that the rotational speed, this angular velocity omega, is proportional to the input voltage. That is to say, a 9-volt battery will make a motor spin 3 times faster than a 3-volt battery. But we also know, and here's a new idea, we also know that there's another property of a motor, and that is its torque, its ability to turn despite the fact that it has some kind of a load on it. That turns out to be proportional to the current that is provided to the motor. And I think at this point we need kind of a picture here of that idea. So here is a battery. Could be a 1.5-volt battery, could be a 9-volt battery, could be 100 volts. The battery is hooked up to the motor, and inside here there's a wound coil that the current goes through, and it creates a magnetic field, and that magnetic field in turn gets this spindle to turn, and of course this disc, which could be gears or anything else out here, will wind up turning. So the current comes in to the motor, kind of disappears inside, we can't really see exactly what's going on, but it goes around and around and around a coil, and then comes back out this tab here and returns to the battery, and the charges keep flowing. The symbol I is used for current, and tau is used for torque. So if you need more torque, if you need to spin something that's a larger load, you're going to need more current for any particular battery. We know that the overall spin rate depends upon the voltage, but the power you need to kind of turn against a load is really linked more closely to the current than it is to the voltage. So let's take a moment to summarize the two things we know graphically. Okay, so first of all, we know that the angular velocity is proportional to the input voltage, or omega is proportional to V. That little symbol there is a proportionality symbol, and we can turn that from a statement of proportionality to an equation by just putting in some kind of a constant here. So omega is equal to some constant times the voltage. And graphically, and we've looked at this before, we can see that that would be a linear relationship whose slope would equal c, and showing that the angular velocity is a linear function of the input voltage. So that's one relationship that we know about. And our new relationship is this one here, okay, about torque and current. Let me just frame that better. The torque is proportional to the input current, and again, we can turn that from a statement of proportionality to just a linear statement. The torque, the ability to turn under a load, is equal to some other constant times the input current. So again, we've got torque as a function of current. It's a linear relationship, and the slope is equal to k. There's one idea that we need to kind of introduce at this point. This seems like a good point to introduce, and that's this, that this is certainly a true statement that there's a linear relationship here between the torque and the current. However, motors will need a minimum current flowing through them before they start to spin, and we call that the no-load current. Okay, so I want to reveal this picture here, which is a slight variation on this one. Okay, yes, torque is going to be proportional to current once we're above the sort of minimum current that we call the no-load current, or I0. Okay, excuse me. So so above and beyond I0, we will have this linear relationship where the slope is equal to k. All right, but there's some value of current for which we will get zero torque. There's just kind of an additional need to initially get the motor to spin. Okay, so that's a little bit of a penalty, if you will, a little bit of a tax to pay as we go through this idea and think about voltage, current, and the electrical and rotational characteristics of motors. In our next video, we're going to take a look at how we can calculate the power input and the power output. We'll look at the electrical energy considerations and the rotational energy considerations.